Oh, so we are going to derive the asymptotic normality from this first order condition. First of all, multiplied by 2 does not matter. You can just divide both sides by 2, and so you may just drop 2, ignore 2. And what we need here is we need to approximate this first order condition to a linear function of theta hat by the Taylor expansion theorem. And we are going to apply Taylor expansion theorem for the moment function g, sample moment function g hat, and exactly this is the Taylor expansion, linear approximation, and we are going to plug this into here. So we are not approximating the whole function, but only this part. So only this part is approximated by a linear function. Then let's see what happens. And remember, theta bar is the intermediate value indicate that exists between theta 0 and theta hat. So there is no difference from the Taylor expansion we used in the previous chapter, and plug that back into this first order condition. We have this thing, and as you know, we are interested only in this guy. So this is what we are interested in, the estimation error, and the other guys must be taken care of. And then we will consider these three terms. First, we will think about this, and second, we are going to apply the central limit theorem on this guy after multiplying the square root n, and then so this guy converges to some constant, and after multiplying square root of n to this guy, we are going to apply the central limit theorem to obtain the normal distribution. And this guy will be converging to a constant, another constant matrix, applying the weak uniform law of large number. So then, using this notation, you can rewrite this complicated form into this. So remember, we are interested in this guy, so we are going to investigate A, B, C, right? And I gave you the basic ideas. A and C converge in probability to some constant matrices, and B converges to some normal distribution. So if Cn is invariable, then exactly this is what we did in the previous chapter. So in that sense, from here, it's pretty much the same. So when you arrive at this point, you should be able to do it by yourself if you understood 100% in the previous chapter. So it's just about how we know the result, but the problem is we need to find the assumptions that are required to show the result. Like it is almost always whenever you write a paper or when you derive some theory, you have to know the answer first. So this is a general advice in your PhD life. So when you write a paper, what is your advisor's job? Your advisor's job is that anyhow you have to have some kind of topic. You have research questions, research topic or data what you want to analyze. Then I think, in my opinion, it is your topic and your paper, but your advisor can see what will happen in that process, in that research. So like if when I was a student, PhD student, when I bring up a new research topic, my advisor used to tell me that, oh, that's not going to be solved, or that will take a lot of time to prove, or it will be too easy, or something like that. So like your advisor knows where is the problem and which step will be more complicated or needed, or it's too difficult for you, something like that. So same, when you see this question, you have to see how you can work through, go through these problems, and then just step by step you have to find the assumptions, collect the assumptions needed, and then just present them in a clean way. That's how you write a theory paper. Anyhow, coming back to the proof, we know the result. We know what we know what we want to show, and we want to show this. So then in the end, I'll spoil the result. So AN, so see this, capital G hat converges to capital G, W hat converges to W, and this will converge to a normal distribution, say normal distribution, normal with variance omega, and see this converges to capital G, W, capital G. We know everything. So I just summarized what I said here, and then just plug them into this form. You are going to have this asymptotic variance, right? So when you see this in the exam or when you read the paper, you may be scared. What is the variance? Why is it so complicated? Right, it's complicated, but like when I summarize how we get the result in a few like paragraphs, I believe you see the big picture, and because you have already studied an easier version in the previous chapter, and then it is just a simple application of the same result. So now you don't need to be scared by intimidated by this formula. Okay, so let's think about the conditions. These are sufficient conditions. I list the sufficient conditions here, and apply the same ideas. I'm not going to explain more. Just the same thing. Everything is the same. So apply the sufficient conditions for each part. Then you will get what you have. What you need. You will get what you need. Right? So I hope you can follow this, and it'll be a good study. So good luck. And then the next question here is, how can we estimate the variance? Now, the variance is given by this form, and even if you know the weighting matrix, suppose that you know the weighting matrix, or at least W hat converges to this matrix, so W is not a problem. But you have to estimate omega, which is the limiting variance of this term, and also you have to have capital G, which is the limit of the derivative. So then how can we estimate that? Not a big problem. So remember, capital G is defined as the population expectation of the derivative. And then we are going to estimate the population expectation by the sample mean, and derivative is known. You can calculate the derivative, but what you can't calculate is the theta zero. Theta zero is the true parameter, unknown true parameter. So replace the unknown true parameter with the available estimator for the true parameter, theta hat. That's it. That is your estimator for capital G. And omega. Omega is another population mean of G prime. It is a kind of variance. This is the variance of G. And the population mean is easy, replace with sample average. And G prime. G is known, you know the function G. but theta 0 is unknown, so replace g hat. So theta hat. So this is how you estimate omega hat. Then this is how you can implement, you can estimate the various metrics. So this is the asymptotic variance and how you estimate the asymptotic variance. So if you are interested, if you are going to major in theory, if you're interested in theory, you have to study it by yourself, investigate why you get the result. And if not, it's up to you. I don't force you to study this if you're not interested. Okay, we are going to continue to the optimal weighting matrix choice. How we choose what is the optimal weighting matrix and how we choose, how we implement the optimal weighting matrix is our next step. So far, these like consistency, asymptotic normality, and variance estimation are just simple extension of the previous chapter's results. So I did not spend much time on this, but what we study in the next video is going to be a new topic, which was absent in the M estimation last lecture. So, and it will be very interesting. It's very interesting manipulation, and the result is very beautiful. Interesting results will come out. So look forward to that. Bye. Thank you for watching.